We now want to consider some maybe miscellaneous topics in the subject of gravity and orbits, and talking about the orbit of the moon around the Earth. There's a major consequence and effect on the oceans of the Earth, and that would be the tides. So if we consider what's happening here, the moon is not just lifting water away from the Earth. We have a high tide on the other side of the Earth. So the moon's gravity is pulling on the mass of water, say 1 kilogram lump of water here, and that pull is stronger than the pull on 1 kilogram of rock at the middle of the Earth, and it's stronger than 1 kilogram pull on the oceans on the far side of the Earth. So there's a difference in gravitational force from the moon on these 1 kilogram objects. A consequence of that is that water will flow along the Earth to try to get underneath the moon's position. So we have water flowing in both directions here. And of course, this is an idealized Earth with a smooth ocean bottom, and the ocean is not as thick as what's shown on this graphic. But water tries to flow along here to get to the position underneath the moon. It turns out the same thing happens on the other side of the Earth. If you would put on vector forces here at the close to the moon, center of the Earth, and on the far side of the Earth, and then you would subtract the vector that's at the center of the Earth from all the other vectors that you might draw here, you'll find that there's a net force tending to make the water flow to these high tide positions, both on the side of the Earth near the moon and the side of the Earth away from the moon. The Earth then is spinning in here. It takes the Earth 24 hours to spin once. It takes the moon 29 days from our point of view to go around to get to the same position with the sun. And as a consequence, an observer here is carried around into these high tide positions. The time between coming to high tide, being carried around by the Earth to where this bulge is a little bit bigger than 12 hours. The moon is moving in its orbit while you're moving the 12 hours, and consequently it's about 12 hours, 20 minutes, something like that. But we do have tides forming because water flows on the Earth, not because the moon is pulling water away from the surface of the Earth. If the sun is aligned with the moon, so we have new moon or full moon phases, this effect gets enhanced. The sun also can create tides. The moon is more important because the difference in the moon's force is a bigger number than the difference of the sun's force across the diameter of the Earth. So at full moon and new moon, we have an extra high tide. And when the moon is at quarter phase, then the tide is not quite as great. Here's an example of the Bay of Fundy in Canada, and same dock, same boat, but high tide versus low tide. And at this particular location, the tides can be over 40 feet, 50 feet. It does depend on the ocean bottom a lot and channels as to the effect, the tidal effect, the difference between high tide and low tide. So this is photography of this bay at high tide, and then at low tide with the waters receded and revealing some of the bottom of that channel. Another major effect is that the Earth has a tidal effect on the moon, and we'll call this tidal lock. If you noticed, if you look at the moon at different phases, you still see these maria, these dark circular areas. The moon spins once on its axis for one orbit of the moon around the Earth. The moon spins once on its axis for one orbit of the moon around the Earth. It wobbles a little bit back and forth, but you can see that these same features are going through all the phases of the moon here, 29 days. You can see that these features basically stay pointed towards the Earth. So the moon is elongated a little bit, and as the moon tries to rotate away from being pointed to the Earth's gravity is stronger on the near side of the moon than on the far side, and prevents that rotation from occurring. A graphic here kind of illustrates this. It's exaggerated, but here's this the green shape pointed towards the Earth, but has some motion back and forth. So our red diagram here, the moon has rotated a little bit. The force on this bulge near the Earth is greater than the force on the bulge away from the Earth. And consequently, there is a corrective force that brings the moon back into alignment. The moon swings back and forth across the equilibrium position where this green figure is drawn. It swings back and forth, but basically the same side of the moon is always facing the Earth. Tidal lock. Tidal lock. The tides have another effect, and that would be to slow the rotation rate of the Earth. The Earth is not spinning as fast now as it was many millions of years ago. The timing on this is 0.0016 seconds per century. 0.0016 seconds per century. So we're used to 24-hour days. We still have 24-hour days next year and the year after that. It's a very slow effect, but it is noticeable in corals. Corals have a growth pattern that has a daily component with high and low tide, and also has a seasonal component. And corals have been investigated and indicate that about 400 million years ago, the Earth was spinning once every 22 hours. Tidal friction has slowed down the Earth. Now we spin once every 24 hours. We can do a little bit of calculations too with solar eclipses and the track that goes across the Earth. There's some historical evidence too there that the Earth's spin rate has changed a little bit over the time we have historical records, but not significantly. The corals give us better information. Another effect of tidal forces: black holes have strong gravity, and if the black hole has a companion star, a star that's relatively nearby, as this star becomes older, it expands, its atmosphere expands, and some gas can leak off of this star and spiral into the black hole. As it spirals down here, it heats up, gets very hot, and emits X-rays. This is one of the prime ways that that black holes are detected, by observing the X-rays. X-rays not generated inside the black hole, but these X-rays comes from material that has not entered the black hole. Of course, you probably are aware black holes are black. No light can escape from the black hole, but this disk of material is outside of the black hole. It gets hot and it emits X-rays that can be observed. Maybe I'll go back here just a little bit too. In the moon's orbiting, the moon is moving away from the Earth. The Earth is slowly spinning down, and as a consequence of that, the conservation of angular momentum that we'll study in this course, as the Earth slows down its spin, there has to be something to compensate, and the compensating factor is the moon moves outward in its orbit to take up some of that angular momentum. And the moon is moving about 1.5 inches a year, 1.5 inches a year further from the Earth. This is documented now with the mirrors that were left behind, 3 by the Apollo spacecraft and 1 by a robot Soviet Union spacecraft. There are mirrors on the surface of the moon. Astronomers can shine a laser at the moon. The light hits the mirror, bounces back. We measure the time for the travel of that laser light, and the distance to the moon can be calculated. And it is true, the moon is moving away from the Earth about 1.5 inches a year. Its orbit is getting bigger. So that's probably just about enough on tides. Talking about Kepler's laws in the early 1600s, Kepler found that planets move on ellipses. Again, Newton's law of gravity, like I've mentioned before, gives a basis for this mathematically, why the force being 1 over r squared, the only path the object can have is an ellipse around the sun, unless you take the circle, that's a special case. But we do have planets moving on circles. Later in the course, we'll study conservation of angular momentum, and Kepler's second law relates to this. As a planet moves past the sun, being closer to the sun, it sweeps out at some imaginary area, and from A to B, if we say that's 1 month, then C to D is also 1 month, E to F is also 1 month, and these areas are equal. As the line gets longer, this imaginary line from the sun to the planet, the path in the orbit is smaller. So the planets move fast near the sun, they move slow away from the sun. This relates to conservation of angular momentum. As the planet moves past the sun, it's close. Its velocity speeds up to keep its momentum constant. When it's far from the sun, it slows down to keep its angular momentum constant. We'll talk about that later. And then the planets here, having the sun at the center, of course, and there's a disk of planets with rotation being important and nearly circular orbits, but still some elliptical nature to them. But let's come back to the Earth. You may be aware of space debris orbiting the Earth from the movie Gravity recently. We have a situation of a lot of orbits of parts of satellites, of old satellites, and then there's this geosynchronous range. This is not really to scale. There's a lot of debris near the Earth. You can barely see the Earth in here. But if we take a look at just near the Earth, radar is used to track these objects in orbit around the Earth, and there's about 19,000 objects in the catalog, with the size here of 10 centimeters, about 4 inches, that they are kept track of because they are moving over 17,000 miles an hour. And some in east-west type orbits, west to east type orbits, some in polar orbits going around the poles of the Earth, and they can crisscross and hit working satellites and can be a problem. So there's a little bit more, some of the concepts for gravity and some of the effects with the tides especially. So keep reading on that and asking questions.